All right, good evening and welcome to this live session on chemical engineering thermodynamics. We're gonna take a few questions from the students today, and I already have some sent to me earlier. So I'll start answering a few of them as we go. The first one happens to be from a student, and he says, I'm getting mistakes when I'm solving problems on ideal gas based on work done because of sign convention. Can you please explain the sign convention once again? So if you recall, we said we need to stick to one sign convention, whatever it may be that we choose. We need to stick to the same sign convention throughout when we solve a particular problem. And all throughout this particular course, we decided that we're going to say that the work done on the system will have a positive sign, and the work done by the system will have a negative sign. So to be able to identify this, the first thing that we need to identify is, what is my system in this particular problem? What is the surroundings in this particular problem? Once I identify the system and the surroundings, the second thing we need to do is see if we are adding work to whatever part of the universe I call as a system. Are we adding work to this system? Then work done is going to be positive. If the system is doing work, or if we are taking work from the system, then the work is going to be negative. And as long as we stick to this particular sign convention, we should be good to solve a problem. Thank you for your question once again. The second question I see is from Wahid Sarwar. He wants to answer, or he wants to know how to solve question number 5 in week 4. I'm assuming that it is the question from the assignment. Remember that we're actually posting these solutions to the assignments online as we go. Some of them, if they are not uploaded already, should be available as soon as we approach the due date. But for this particular question, number 5 in assignment 4, it says a steam turbine operates reversibly and adiabatically. It takes superheated steam at particular conditions and discharges at 1 bar. And the flow rate of the steam is given. And we want to calculate the power output from the turbine. So to be able to do this, we know that the discharge conditions, it is saturated vapor at 1 bar. And once we know the discharge conditions, we will be able to calculate the entropy. And once we know the entropy, because the process is reversible and adiabatic, remember we said for a reversible adiabatic process, it also happens to be what is called as an isentropic process. The entropy change across the process is going to be 0 because it is both reversible and adiabatic. If the entropy change is 0, then at the inlet, I know the entropy because I know the entropy at the outlet already. Once I know the inlet entropy and the inlet pressure, I would know the inlet conditions. I can look up the steam tables and calculate or find out the inlet temperature, inlet enthalpy, etc. So in that sense, if I use the steam tables, I would know both the inlet enthalpy and the outlet enthalpy, and the difference is going to be the work done by the turbine in this particular case. So that should help you to solve this particular problem. All right, thank you. Let's see. If we have another question, can we look at another question, please? It says, how can one distinguish between a cyclic process and a reversible process, since both of them finally return to their original state. These are two different processes. A cyclic process is one where you start from a particular state A, go through a series of steps, say A to B, B to C, and then back to A. That is a cyclic process, right? Can I have the PowerPoint, please? Right. So let's draw a cyclic process. Maybe that will help you to understand the concept easily. So, right. So in a cyclic process, I'm at a particular state A. I go to state B, then to state C, and maybe, so let's put some arrows to get the direction, right? To state D and back to state A. So this whole process going from A to B to C to D back to A would give me a cyclic process. Now, a cyclic process can be reversible, it can be irreversible. Reversibility and irreversibility have nothing to do with the cyclic part of this particular process, right? Cyclic in that sense only means that we end up with the same initial state as we started with after we complete the whole series of steps in that particular process. So I hope that answers your question. Let's see. Do we have another question? Where are we getting this? Can I have the question on the chat window, please? Okay. Maybe I think the question is not complete. All right. So I think this question number 5 for week 4, if I understand it right, the trouble you're having is to be able to get the temperature at the inlet, because you need the temperature, you need 2 conditions at the inlet because it is in a superheated state. You need 2 conditions at the inlet to be able to get the enthalpy and hence calculate the work done. You're asking that only the pressure, which is 20 bar, is given. So how is it possible to calculate the enthalpy, right? I hope I got that right. So the trick, like I said, is the outlet conditions are given. It is a saturated vapor, so you just need one condition, the pressure is given. So we can calculate all the thermodynamic variables at the outlet, including the entropy. And because it is a reversible and adiabatic process, and because it is a reversible and adiabatic process, the entropy at the inlet is same as the entropy at the outlet. Remember, we already calculated the entropy at the outlet from the saturated condition at 1 bar. And once I have the entropy at the inlet, then I have 2 conditions, a pressure and entropy at the inlet. Once I have these 2 variables, I should be able to calculate any other thermodynamic property. I hope that answers your question, Mahit. Thank you. Okay. There seems to be still an issue with some questions in week number 1. There was a minor correction with the software and the range of the answers we have provided for getting the credit. It seems to have been fixed. I was told that it has been fixed. If you still have an issue, please send us an email and we'll try to sort out the issue and credit for the correct answers. So we'll take care of that. Please send us a separate email and we should be able to handle that fairly easily. I have some pending emails with me. We're working on that and you should be able to sort that issue offline. Thank you. So the next question is, what is the definition for enthalpy? Right? Most of these thermodynamic variables, like we discussed, you might have realized by now, provide us easy ways and simpler equations to work with. In that sense, enthalpy is essentially the U internal energy term plus the PV term, right? PV also is a form of energy, right? So you add internal energy U plus PV, and we call this total value of U plus PV as the enthalpy. And if you recall, when we have performed the energy balance on a flow process, it turns out that you get an internal energy term and you get a flow work term, and you add these two terms, what we have is the enthalpy term. So in that sense, it will help us to handle some of the equations in an easier way. So if you think about it, it's a convenient variable to work with in certain cases. Thank you. Okay. All right. So I'm asked if we can clarify the difference between steady state and equilibrium. I think we have a lot of students who have trouble identifying these two. That's the reason when I gave this example, I provided an example in the lecture videos, but briefly, equilibrium is the case when we do not have change with time, and we also do not have the tendency to change, right? Whereas in steady state, things don't change, or thermodynamic properties, thermodynamic variables do not change with time. But then if you isolate the system from the surroundings, then they have a tendency to change and reach the final equilibrium state. Whereas once we say we are at equilibrium, then of course things don't change with time, but in addition, they don't even have the tendency to change with time. So irrespective of whether they're isolated from the surroundings or not, unless we don't change the given conditions, then they don't have tendency to change with time. They don't have tendency to change. So that's the distinction between equilibrium and steady state. And remember that we provided an example of a rod which is dissipating heat from a hot body to the ambient atmosphere at steady state conditions. But the moment we isolate this rod from the surroundings, the temperature across the rod is going to change and reach its final equilibrium value, which is going to be uniform throughout the rod. So in that sense, it is a steady state scenario and not an equilibrium scenario. Thank you. So one of the questions that I'm asked is why there are no multiple choice type questions in the assignments. What we do in thermodynamics, like you have seen, is mostly work with numbers. Whatever the questions I gave so far do not involve any derivations. It's much easier to work with the numbers and appreciate the facts in whatever chapters we have covered so far. And that's the reason, because the answers are in terms of numbers. I thought it's much easier to have just a fill in the blank type questions wherein you can enter a numerical value. But as and when there is a need for derivations or multiple choice questions, I would of course incorporate them into the assignment. Thank you. The other question I'm asked is to give some daily life examples for whatever we have done in the course, or we're going to do in the course. Remember early on in the first introductory video, I had provided multiple examples where thermodynamics plays an important role in chemical engineering, especially in terms of phase equilibrium, reaction equilibrium, in separation processes, etc. So to be able to appreciate the role of thermodynamics in phase equilibrium sort of conditions, it is necessary that we have the basics that are required to extend these concepts to phase equilibrium scenario. And so far in the course, that is what we have done. We have defined a variety of thermodynamic variables. We looked at how they can be calculated for various scenarios, if it is an ideal gas, if it is not an ideal gas, if it is a liquid, etc. Once we understand these concepts and then move on to the phase equilibrium or reaction equilibrium scenarios, then it becomes necessary to calculate, let's say, something like a Gibbs free energy for the liquid phase, Gibbs free energy for the vapor phase, and equate these two to obtain the equilibrium. So to be able to do that, the first step is to be able to define what Gibbs free energy is, then know how to calculate them for pure components, for ideal gases, for non-ideal gases, for liquids, then know how to calculate it for a mixture of species, and then apply it to the desired scenario. The other practical application that I can think of, just with whatever we have worked so far, although it is usually not discussed in chemical engineering thermodynamics, is power and refrigeration cycles, the calculation of the use of thermodynamic diagrams, calculation of change in enthalpy, entropy for a process, for a cyclic process, and use them to develop refrigeration cycles or power cycles, which is more of classical thermodynamics, of course. I hope that answers the question. As we extend this discussion more into the coming weeks, then you will see how these are readily translated into chemical engineering applications. Thank you. All right. The other question I have is, can the equation ds equal to dq over t be applied for an irreversible process? If not, how does one determine the entropy change for an irreversible process? Remember, entropy change, entropy is a state function. So all that matters is the two states, the initial state and the final state going from A to B. If one is interested in determining the entropy change for this particular process, one of the ways to do it is use dq over t, but then that dq over there should be along the reversible path between A and B. As long as we have, or we know the value of q along the reversible path between A and B, I should be able to calculate ds, although the process itself is irreversible. On the other hand, as we have seen so far, we can calculate the change in entropy using the given conditions, the temperatures, the pressures, etc. Calculate the entropy change for an ideal gas, for a non-ideal gas, to involve what is known as the residual entropy term, and then calculate the change in entropy for the process based on the given information of temperature, pressure, or whatever other thermodynamic variables are. But if one is, of course, interested in calculating it using the heat exchange, then, like I said, the easiest way is to be able to determine how much heat would be exchanged if the process were reversible, and then calculate delta S using that reversible value, or using the Q along the reversible path. I hope that answers your question. Thank you. Can I have the next question? Okay. Wahid still says that solving the problem the way you suggested, the answer doesn't come in the provided range. I think we're still talking about question 5 in assignment 4. We'll definitely upload the solution as soon as the due date approaches, and then if you still have an issue at that time, please send us an email and we can work on that. Thank you, Wahid. Chandra Kiran says, why we use only Gibbs free energy but not Helmholtz free energy through temperature, though temperature and volume are also measurable properties? That's a good question. I kept emphasizing that we're interested, or one of the goals of working through these set of equations is to be able to relate those properties that are not directly measurable in terms of properties that are directly measurable. So in that sense, yes, temperature and volume, of course, are measurable properties. And Helmholtz free energy, in that sense, provides an interesting, is an interesting thermodynamic variable. But as we move on into phase equilibrium, you will see that it gives free energy plays a vital role in phase equilibrium calculations, and that's the reason we emphasize more on Gibbs free energy rather than Helmholtz free energy, in addition to, of course, T and P being measurable. Thank you for that question, Sai. Sai says, can you explain Gibbs free energy function of temperature and pressure for for pure substance? I'm not sure if I got that question correctly. Can you elaborate while I try to write the Gibbs free energy for a pure substance, for a homogeneous substance? If you recall, dg, we have written it as vdp minus sdt, right? Can we use the next slide? Yeah, okay. So for a pure homogeneous closed system, the way we have written the change in Gibbs free energy, it is dg is vdp minus sdt. Of course, all of these are molar quantities, so we have related the change in Gibbs free energy to change in pressure and change in the temperature. So I don't know if that answers your question, Sai, or you wanted to know something else. Let me take another question from an offline query. What actually entropy means? What is the significance and importance? All processes in universe are irreversible, but majority thermodynamic study is seen on reversible processes. Then how to apply it for practical irreversible processes? So let me answer the last part of the question first. All processes in the universe are irreversible, but majority thermodynamic study is seen on reversible processes. Then how do we apply it for practical irreversible processes? So let me write a couple of quick equations while I answer this question. That one. Yeah, thank you. Now, let's write the fundamental property relation for internal energy change. du is can I go back? And then let's get the slide. Right? So the fundamental property relation du is TdS minus PdV. If you look at this relation, the way we got it is from the first law. And for a reversible process, this is dq plus dw, right? dq is TdS, dw is negative PdV. So du is dq for a reversible process plus dw for the reversible process. But because u is a state function, it turns out even if I have an irreversible process, then along the same, between the same two states A and B, then du is also going to be dq for the irreversible process plus dw for the irreversible process. Now, if I look at these two equations, 1 and 2, it turns out that sum of dq plus dw for a reversible and irreversible processes is same. And because it is same, I can, even for an irreversible process, du is going to be TdS minus PdV. So this du being TdS minus PdV is always true whether the process is reversible or irreversible. It doesn't really matter. So only thing that differs between the two processes is that two individual terms, TdS and minus PdV, can be identified with heat and work. For a reversible process, they cannot be identified with heat and work for an irreversible process. So irrespective of what the type of processes, the fundamental property relations we have looked at, they do not, they will not change whether the process is reversible or irreversible. Now, coming to the first part of your question, what is the significance and importance of entropy? Remember, in one of the lectures we talked about, entropy generation, right? We have done an entropy balance, and we have written an equation for entropy generation, right? And for a reversible process, this entropy generated term is going to be equal to 0. For an irreversible process, it's going to be positive. It's going to be greater than 0. So in that sense, the entropy generated is going to be a sort of measure of the irreversibility of a particular process. I hope that answers your question. Thank you. All right. We have Sai back with his question. He says, sir, I mean, how Gibbs free energy varies with temperature and pressure for solid, liquid, and gaseous, for example, water. One can calculate the Gibbs free energy change. Once in the coming lectures, we're going to look at the phase change, and once we know how to calculate the change in thermodynamic properties when a phase change occurs, we should be able to calculate it going from one phase to another and across the phases, going from a certain condition in a gaseous phase to a different condition in a liquid or a solid phase. This, of course, is true not just for Gibbs free energy, for enthalpy, entropy, etc. We should be able to do those calculations in the next 1 or 2 weeks. But otherwise, the fundamental property relationship itself, dg is vdp minus sdt, that will not change depending on the phase. The change in Gibbs free energy is always going to be vdp minus sdt, right? That itself will not change. How we calculate these changes for different scenarios, we're going to look at that in the coming weeks. Sai also says, what is the use of law of corresponding states? The corresponding states, we looked at a 2-parameter and 3-parameter theorem of corresponding states. It simply says, the 2-parameter theorem says that if 2 different substances are at the same reduced temperature and pressure, then they behave identically in an identical manner. Their molar volume, etc., are going to be same. Whereas a 3-parameter corresponding states theorem adds an additional parameter to account for differences in polarity and size of the molecules, and that is accounted through a parameter known as omega, or the eccentric factor. And it says that if two different substances with the same eccentric factor are at the same reduced temperature and pressure, then they behave in a similar manner. That's the essential difference between the theorem of corresponding states. And we can use this theorem of corresponding states to do property calculations. We're going to look at that in the next week lecture. Thank you. Himanshu says, sir, I was learning about the application of Gibbs theorem in that under the internal energy, we took T and P as fundamental variables instead of T and V. Please explain. I'm not sure if I got that question, Himanshu. Can you please elaborate? What do you mean by we took T and P as fundamental variables? For du for internal energy, the canonical variables for internal energy of du is TdS minus PdV. So U, S, and P form a canonical set, and for Gibbs free energy, it is dg is VdP minus SdT. So G, T, and P form a canonical group. So this transformation allows to change the grouping, canonical grouping, and then the derivatives accordingly change. I hope that answers your question. I'll be able to help you out if you can elaborate what you exactly mean by Gibbs theorem and the internal energy. We took T and P as fundamental variables. Thank you. Muhammad says, what is the significance of chemical potential? Chemical potential is something which we still did not discuss about in the previous lectures. We're going to do so maybe in another 2 or 3 weeks. Once we talk about thermodynamics of mixtures and solution thermodynamics, we'll start introducing the chemical potential. And at that time, it might be easier for me to explain, having covered solution thermodynamics. We have another live session maybe in a month or so, and I'll be happy to answer your question at that time. So hang on there. Thank you. RGT. Sumedha says applications of Maxwell equations and thermodynamic diagrams. Those are two different things, if I got your question correctly. For the Maxwell's equations, we said we relate the derivatives of properties that cannot be directly measured to the derivatives of the properties that I can directly measure, such as temperature, pressure, and volume, things I can measure. Now, the other side of the Maxwell's equation, we usually have derivative of entropy, etc. So we can relate these two things. In that sense, it provides us an easy handle to calculate changes in entropy simply by relating it to changes in temperature, pressure, and volume. On the other hand, the thermodynamic diagrams we looked at provide elaborate information over a wide range of temperature and pressure, the details such as molar volume or specific volume, molar enthalpy, entropy, etc. are listed or provided on the diagram, right? So once I have this thermodynamic diagram and I know for a single phase system, if I know two thermodynamic variables, say temperature and pressure, or temperature and enthalpy, etc., I should be able to calculate all the other thermodynamic variables such as entropy, molar volume, or specific volume, things like that, fairly easily by looking at the thermodynamic diagrams. I hope that answers your question, Sumedha. Thank you. Okay. I have another question. It says, we want to know about the concept of entropy generation. Can I have the PowerPoint screen, please? So what we do is essentially write a entropy balance, as it is called. And unlike a material or mass balance or energy balance, entropy can be generated. So essentially, the difference in the entropies, so of the inlet and outlet streams, let's say, is given by delta of the flow streams is n dot S. This is the specific or molar entropy multiplied with the molar flow rate n dot for the flow streams. So this delta is, let's say, something like streams going out minus streams coming in. For all the streams, if there are multiple streams, then we sum up all the inlet and outlet streams, get the total entropies, and then get the difference between the outlet and inlet streams. That would be delta n dot S for the flow streams, minus the entropy exchanged with the surroundings is Q dot over T sigma, right? Plus the rate of entropy accumulation within the control volume, if the size of the control volume is n moles, then dNs would be the total entropy within the control volume, and the rate of accumulation is going to be dNs for the control volume over dt. So this is the total entropy in minus out within the control volume plus the accumulation terms, and this will equal the rate of entropy that is generated. Right. So this the sum of all these terms in minus out plus the accumulation would give the rate of entropy generation in a particular scenario. I hope that answers your question. So with that, I thank you all for participating in this live session. I hope you enjoyed it. We look forward for more participation in the future. We're going to go live again soon. Thank you again. Enjoy the course until then. Bye-bye.